3, Chapter 5, Section 1, Exponential Functions and their Graphs. Transcendental functions are functions that are non-algebraic, and as we get into exponential and logarithmic functions, these are transcendental. Some other examples, well, first of all, exponential that we're going to be doing in logarithmic. Trigonometric functions are also transcendental functions. So pretty much for the rest of the year, we're going to be dealing with these transcendental functions. An exponential function is a function where the independent variable, where x is an exponent or is a part of the exponent. Here's the basic function, f of x equals a to the x. A is greater than 0, but not 1, so it can be a fraction between 0 and 1, and then it can be anything greater than 1. And x must be representative of a real number. A is called the base, and the basic graph looks like this. Y equals a to the x. This is considered an exponential growth function because as you look at it from left to right, it's increasing. And this would be an exponential decay function because as you look at it from left to right, it's decreasing. Notice that both of them cross the point 0, 1. Also notice that the x-axis is a horizontal asymptote. In other words, y equals 0 is a horizontal asymptote because you cannot raise a number other than 0 to a power and get 0 for the answer. Notice that the difference between the growth and decay is the sign on the power. Note that with the exponential growth, the growth begins slowly and then it picks up speed as time progresses. For example, compounding interest in a bank account, at first the money doesn't grow very quickly, but the more that it grows, the more that it compounds, the faster the growth occurs. With exponential decay, the decay begins quickly and then slows over time. The depreciation of a car is like this. A car, when you buy a brand new car, the value goes down very, very quickly at first, and then over time it tends to level off and not go down so quickly. Exponential functions are one-to-one, so they do have inverses that are also functions. That means that every x value goes to its own unique y value. So we're going to be doing some translating, and this actually is the same as we've been doing all year, so no big surprises there. Adding or subtracting a number to x, and again, remember this will be in the power now, moves the graph left or right, and it's the opposite of the way you think. So if you add a number to x, it's going to move it left. If you subtract, it'll move it to the right. Adding or subtracting a number to the function is going to move the graph up or down. When you add or subtract a number to the function, it not only moves the curve up or down, but it's going to move that horizontal asymptote as well. So we said that y equals 0 is the horizontal asymptote for the basic function, but if you add a number or subtract a number, that's going to move also. In fact, the number that's added or subtracted actually becomes the new horizontal asymptote, which is very convenient. We have a special base called the natural base. It's symbolized by e, and here we have a decimal approximation of it. Like pi, it is an irrational number, so it has no end and does not have a repeating pattern, so it cannot be accurately represented by a fraction. The number is named e for Leonard Euler, who discovered it, and it has special properties in calculus. In fact, it's very easy to work with in calculus. F of x equals e to the x is called the natural exponential function, and you can find it in two places on your calculator. The first place is it's a second function of the ln, the natural log key. You see it there. And the second place is that it is the second function of the division key. Now you may wonder, well, what's the difference? Notice that the one on the natural log says e to the x. When you use the key, this key for it, what it does is it puts an e on there, and then it gets you ready to put in a power. It gives you the cursor will be set up to do a power for you. If you use the one on the division key, then you have to use the power key in order to put it to a power. It doesn't matter which of these two you use, but you must use one of these two. Do not use the alphabet key to represent e. It is specifically, these two keys are specifically made for that purpose, and they have the value of e stored in those slots in the calculator. So it's really important to use one of these two for some applications. We have a compound interest formula, which I will give you these formulas. You just need to know how to use them. So A equals P times 1 plus R over N to the NT, where A is the amount in the account after a number of years. P is the principal, which is the starting amount. R is given as a percent, which you need to change to decimal, and that is the rate of interest. N is the number of times the interest is compounded per year, and T is the number of years. We also have a formula for continuously compounded interest, which is A equals PE to the RT. I also call this the PERT formula or the shampoo formula, but it's principal times E to the rate. All right, here's some problems to try, so see if you can do them. And pause the recording and then resume and see how you did, and we'll talk through them. Okay, so with the 1-to-1 property, what we're going to do is we're going to change the 27 to 3 to the third, because 27 is 3 to the third. Now that our two bases are the same, what I can do is say, oh, well, if 3 to the x plus 1 equals 3 to the third, then x plus 1 must be 3, which means x must be 2. And the second one, use the graph to describe the transformation that yields the graph of g. Well, what we're going to do is notice the difference. 1 has been added, so it's going to be the graph of f moved up 1. All right, now try these. Pause the recording, give it a try, and resume to check your answer. This one's again pretty easy. The bases are the same, so the powers must be equal. So we just set the powers equal to each other and solve for x, which is 1/3. The second one's a little more complicated. If you haven't tried that, then pause to do it. If you have already tried it, then keep the recording going and we'll talk about it right now. Oh, sorry, I didn't give you the table, but there is the table. And so we have time for 10, 20, 30, 40, 50. All you're really doing is you're putting this information into the continuously compounded interest formula. So your principal is going to be 12,000. You see it there, e to the 0.04 times t, and then you're just going to replace t with 10, then 20, then 30, then 40, and then 50. Okay, try this problem. Again, another continuously compounded interest problem. Pause the recording, give it a try, and resume to check your answer. And we get, using our formula, $212,605.41. Okay, now we have a problem about a drug being injected into the bloodstream. We have 300 milligrams per milliliter after T hours. The concentration is 75% the level of the previous hour. Find a model for the concentration of drug after T hours. Okay, this is a little tough, so we'll kind of go ahead and just talk you through it. Our model is going to look like this. C of t is 300 times 0.75 to the t power. Notice what we have. We have our initial amount, which is 300. That's like our principal. And then our base is 0.75, so that goes there. And then the t is the power. And then they want us to determine the concentration of the drug after 8 hours. Well, A was the hard part. So if you can get A, B, you're just going to put in 8, and we get 30.03. Okay, use the properties of exponents to determine which functions, if any, are the same. So you know our properties of exponents. Kind of fiddle around with these. Which of these are the same? Are they all three the same, or two of them, or are they all different? Pause the recording, see what you think, and resume to check your answer. Okay, so f of x is 3 to the x minus 2. Remember when you multiply, you add the powers? Or you could even think of it when you divide, you subtract the powers. They multiplied. They said, okay, that's the same as 3 to the x times 3 to the negative 2, which is like 3 to the x times 1 over 3 squared. Well, 1 over 3 squared is 1/9. So it's like 1/9 times 3 to the x, which is h of x. But g of x is way off, so it's nowhere near g of x. So f of x and h of x will be the same thing.